Hey, my name is Piotr and I'm excited to present our latest paper, Efficient Transformers with Dynamic Token Pooling. This is a collaboration between researchers from University of Edinburgh, Pathway, NVIDIA, and University of Wrocław. Transformer language models are the state-of-the-art backbone for most NLP applications. Despite this, they remain constrained by their quadratic complexity with respect to the sequence length, which makes processing longer inputs very costly. To remedy this shortcoming, the research community proposed more efficient variants of transformer architectures. These rely on either sparsifying the attention mechanism or shortening the input in the intermediate layers. In this work, we focus on input shortening and more specifically on token pooling methods. Token pooling for autoregressive language models has been first introduced by the hourglass architecture. Hourglass is a hierarchical and symmetric model similar to units. It starts with a sequence of tokens which is first processed by a small block of transformer layers and then pooled into a shorter sequence via fixed-length min pooling. The shorter sequence is then processed by another block of transformer layers, and this can go on recursively many times. After a series of shortenings, they upsample the sequence back to the original resolution. In language modeling, our objective is next token prediction, for which we need the same number of tokens we begin with. So whenever we pull a sequence of tokens, we need to then upsample it back. Nevertheless, pooling groups of fixed size, like it's done in Hourglass, is suboptimal in several respects. Firstly, elements of a sequence often carry different degrees of information. For instance, we have silence versus voice in speech signal, or background versus objects in vision. Similarly, in language, some tokens are easier to infer than others. Ideally, the model should rely on the same abstractions as humans when processing language, and do so by allocating resources in proportion to tokens' difficulty. Secondly, groups of fixed size are misaligned with linguistic primitives, such as words or phonemes or morphemes, which vary in size. To this end, we propose a transformer variant that jointly performs language modeling and learns how to pull a sequence of tokens into groups of variable size. Specifically, we tackle the following research questions. Can we jointly improve efficiency and performance of transformer language models with the right inductive biases? How to extend the hourglass architecture with fast pooling into groups of variable size? What are the pros and cons of different segmentation methods? Finally, what is the impact of dynamic pooling in languages with different morphological types? In our model, which we simply call dynamic pooling transformer, we follow the hourglass backbone with one shortening and one upsampling. Instead of pooling tokens into groups of fixed length, we introduce a lightweight boundary predictor which is conditioned on the hidden representations after the first block of transformer layers. The boundary predictor outputs a binary sequence, which we then use to group the tokens. Specifically, whenever we encounter one, we close the previous group and start a new one. After processing the shortened sequence by the middle block, we upsample the tokens by simply duplicating them and augment them with a residual connection from before shortening. Training a boundary predictor is not obvious, as we need to make discrete decisions about whether we close a group of tokens or not, and this decision is inherently non-differentiable. One of the methods we propose to train the boundary predictor is by making it follow the spikes in the conditional entropy of our target distribution. Intuitively, peaks in the conditional entropy provide indications of surprisal and can serve as natural boundaries between segments. Empirically, as we can see on the figure, entropy spikes in language models overlap with word or morpheme boundaries to a significant degree. Apart from the entropy spikes, we consider two different ways of training the boundary predictor. supervised learning by tokenizers such as PP or Unigram, or end-to-end learning through stochastic re-parameterisation, specifically Gumbel sigmoid. Additionally, we also test natural data boundaries such as white spaces, which separate words in many scripts. In terms of our experiments, we evaluate the effectiveness of dynamic pooling on 4 morphologically diverse languages. We compare our approach against an established baseline, that is 12-layer transformer XL. Our model has the same architecture, and the only differences are extra shortening and pooling operations which are controlled by the boundary predictor. As you can see on the screen, most layers in our model process the shortened sequence, which significantly reduces the compute requirements. For example, in most of our experiments, our model is twice as fast and uses half of the baseline's memory. Our results on language modeling show that dynamic pooling transformer outperforms vanilla transformer and fixed-length hourglass model in terms of both speed and accuracy. In the paper, we include a number of ablations, including scaling study and performance efficiency comparisons of different pooling approaches. Among others, we find that the gains of dynamic pooling do not vanish at larger scales, and that dynamic pooling pushes the efficiency performance Pareto front of transformer language models. So, to conclude, in this paper, we propose a new transformer variant that jointly performs language modeling and learns how to pool a sequence of tokens into groups of variable size. Dynamic pooling transformer is both faster and more accurate than vanilla and fixed pooling transformers. In the future, we would like to explore combining input shortening with subquadratic attention, and also we'd like to test multi-level dynamic shortenings. Thanks for listening. If you want to know more about this work, scan the QR code, which will redirect you directly to our paper.